Okay, this is Mr. Peterson. I'm going to be going over section 7.3 from Math 31, and this covers the Pythagorean theorem. And before we get to that, you have to have a little bit of background. So we'll be looking at square roots. Okay, if you remember maybe in elementary school when you were learning your multiplication table, you had numbers down the side, 1 through usually 12, and then numbers across the top. Well, the diagonal going from 1 times 1 to 2 times 2 to 3 times 3, those were numbers that are called perfect squares. So, for instance, 9 is considered to be a perfect square because it's 3 times 3. The next perfect square is 16, and that would be 4 times 4. And most of the time in elementary school, you learn all the way up to 12 times 12. So the last perfect square that I have listed here is 144. But there's no reason that this list couldn't indefinitely extend. So for instance, 45 times 45 would be some number, and that number, because you're multiplying 45 by itself, would be described as a perfect square. So when you go backwards and figure out what it is that you square to get the number, that's called a square root. So for instance, 36 is a perfect square, and its square root, you can see the symbol for the square root there. It's kind of a check mark with a hat. The answer to the square root of 36 is 6, since 6 times itself, or squared, is 36. 81 would be 9 times 9, so the square root of 81 is just 9. And the square root of 121 is 11, since 11 times 11 gives 121. Okay, so these are called perfect squares, but not all numbers are perfect squares. For instance, the square root of 20 is not so friendly. We know that 3 times 3 won't give 20, it's too low. 4 times 4 likewise is too low. But when you get to 5 times 5, you know you've overshot it, since that's 25 and is bigger than 20. So the square root of 25 lies between 4 and 5. 4 times 4 is too low, 5 times 5 is too high. Now the way a mathematician writes down on paper that it's between two values is he or she puts two less than signs around the number, and then he puts the smaller one on the left and the bigger one on the right. And you really kind of think of this as two things. 4 is smaller than the number, and the number is smaller than 5, which puts the value square root of 20 between 4 and 5. Now, if you take your calculator and you type the square root of 20, you'll get a long, ugly-looking number. If you round it to 2 decimal places, it's very close to 4.47. And that means if we took 4.47 times 4.47, we'd get something very close to 20. It's not exact because this number is called an irrational number, and as soon as you round it, you're just getting an estimate. But it's a pretty good estimate if you round to the 100th place, so that's what I'm going to be doing on most of these. Okay, square root of 54. Well, I know 6 times 6 doesn't give 54. That's too low. 7 times 7 is closer, and 8 times 8 overshoots it. So the square root of 54 is bigger than 7 and smaller than 8. In other words, it's between 7 and 8. And if you just simply type square root of 54 on your calculator, it'll give you approximately 7.35. Now, you may notice that I used the squiggly version and the other version of approximately equal to. One is an equal sign with a dot above it, and the other is an equal sign that's doing a hula dance. Okay, square root of 75, you're just supposed to estimate this on your calculator, so just type square root of 75, and you'll get approximately 8.7. We're supposed to round to the nearest tenth in this case. And square root of 132, 11 times 11 is too small, 12 times 12 is too big, and it actually does round to right in between those numbers. You shouldn't assume that if it's between two values, it's a 0.5 value. That's not true. For instance, here, 1 times 1 is too low, and 2 times 2 gives 4. That's too high. So I know it's between 1 and 2, and it's actually about 1.4. 1.414, so it rounds off to 1.4. Okay, that leads into what we were hoping to actually learn in this section, and that's how to use probably the most famous theorem in mathematics. It's called the Pythagorean theorem. It's over 3,000 years old. Now this talks about the relationship between the side lengths of a right triangle, and we have one pictured here. It's got two sides that make a 90-degree corner, and usually that 90-degree corner is indicated with a little mark like that, little box, or you can actually just write 90 degrees in that corner. But if it doesn't have a 90-degree corner, then you just simply can't use the Pythagorean theorem. The Pythagorean theorem talks about the side lengths of a right triangle. So the triangle on the right over here, that's not a 90 degree, this is not a 90 degree, and that's not a 90 degree. So Pythagorean theorem, you can't apply to that triangle. Okay, now the terminology is important. The two sides that make up the 90-degree corner, that side and this side, they're called the legs. And we always label them A and B. Or they should be labeled A and B. That's the most common way to label them. The other one is called the hypotenuse. It's a Greek name, and it's the longest side of the triangle. It's also the one that's across from that 90-degree corner. And the hypotenuse, in the Pythagorean theorem's classic way of writing it, is always labeled C. Okay, so which one's A and which one's B? They're the legs that form the 90 degree, but how do you tell which one's A and which one's B? And the answer is it doesn't matter. The formula is down here. Has a plus sign in between those two, and plus sign can be turned around. Addition is not sensitive to order. So if you said b times a, b plus a, b squared plus a squared instead of a squared plus b squared, it wouldn't matter. Okay, the sum of the squares of the lengths of the legs of a right triangle. So that's a mouthful. The sum of the squares of the lengths of the legs, the ones that make the 90-degree corner, is equal to the square of the length of the hypotenuse. Okay, so it's almost as easy as A plus B equals C, but not quite. If you write down A plus B equals C, that's false. But the Pythagorean theorem simply squares those, and then the equation is true. Okay, there's two types of problems that we're going to deal with here. One is where the hypotenuse is the missing length. So here you're going to have C that's missing. And you can tell that it's C that's missing because the right angle there, those are A and B in any order. I'll just arbitrarily choose that one as A and this one as B. So now I know 10 squared, A squared, plus B squared, 24 squared, is equal to C squared. Okay, that'll take us down to, we're supposed to square first, 10 times 10, 100. And then if you take 24 times itself, 24 squared is 576. Combining this gives 676. And we're almost there. We don't have C yet. What we have is C squared. So you counteract the squaring by square rooting. And on this side you get C, and over here you get equals 26. So square root of 676 is 26. So that length is 26 meters. You should probably put the units on there, but I don't have room on this problem. Okay, the 90-degree corner is right there, so this must be A and B here. And again, it doesn't matter which one you label A and B, but you do have to label the hypotenuse C. So it's going to be A squared plus B squared equals C squared, which is 80 times 80, 6,400, plus 60 times 60 is 3,600. And that's equal to c squared. And when you add these, you get 10,000. Square root both sides. And you find out that c is equal to 100 inches in this case. That's the length, 100 inches long. Okay, I'll do another example like this before I, in a separate video, show you the second type, type 2. Okay, A is 4 and B is 8. And sometimes I have students take this little angle bar there, the little square thing there, and I have them extend it and make a plus sign out of it. And that tells you that those are the two side lengths that are going to be added after you square them. So it's going to be 4 squared, there's the plus sign, 8 squared equals c squared, and I'll label the c over there. C is always the longest side of the triangle. That's another way to kind of recognize it. So what we have here is 16 plus 64 is c squared. Add those and you get 80 equals c squared. Now that's really close to 81. If it were 81, I wouldn't need my calculator because 9 times 9 would be 81. This thing's a little less than 9. I know 9 times 9 would give 81, a little higher. So this is slightly less than that. And if you take the square root of both sides, then you end up with about 8.9, which is pretty close to the 9 that I said earlier. So 8.9 miles, that's the length of the hypotenuse. Okay, example 4 is actually not a triangle, but if you draw a diagonal across that rectangle, you can see that it's pretty easy to see there. You got a right triangle going on. So the side lengths that make up the 90-degree corner are A and B. And we're calling it X this time instead of C. The hypotenuse is the longest side of the triangle. Okay, so it's going to be 13 squared plus 15 squared equals X squared. Normally we'd put a C there. 169, that's what 13 times 13 is, plus 225 is equal to X squared. When you add these together, you get 394. And all we have to do is square root both sides to finish the problem. So over here you get X, and that's because the squaring and the square rooting undo each other. And the square root of 394 is about 19.8. And your calculator will tell you that. Okay, so it's about 19.8 inches. All right, we will pick up on the next video with a continuation of these notes. We'll be looking at how to use the Pythagorean theorem when you're missing one of the leg lengths.